What's up, guys? It's me, Sir Ernest, and today we're going to calculate the moment of inertia of a thin rod. So here, let's assume that a thin rod has a uniform density. So that means the density is a constant. So if we have a thin rod, that means the thickness of this rod will be neglected in the calculations. So this problem will now be reduced into a one-dimensional problem. Now let's assume that the rod is situated along the x-axis. And let's say the axis of rotation is about the z-axis. So for example, if this is your y-axis, therefore the axis perpendicular to the screen would be your z-axis. So this will be our axis of rotation. So let's set that the length of the thin rod is A and the mass is M. So therefore, the density is given as rho, and this is equal to M over A times A. Here, the axis of rotation is perpendicular to the rod, okay? So, as we already said earlier, the moment of inertia can be calculated as r squared times dm. Then we take the integral of that to get the total moment of inertia. So in this case, we're going to consider a line element whose infinitesimal width is dx. So this will be our dl. So in this case, this becomes integral of dm would be rho dl or dx. So what is r squared? So r, as I mentioned earlier, is the distance from the axis of rotation from the element mass. So if this is your element mass, the distance r would be the x distance away from your origin. So this is x. This becomes x squared. And the integral will be along the x-axis. So the limit of integration will be from 0 all the way to a. So we just write it here from 0 to a. This is now how you set up your moment of inertia. Let's solve this accordingly. So Iz, or the moment of inertia along the z-axis that is perpendicular to the rod passing through the origin, will now be equal to rho times the integral of x squared dx integrated from 0 to a, and this is equal to rho a cubed over 3, or simply 1/3 m a squared, where m will now be equal to rho a. So for a thin rod whose axis of rotation is perpendicular to the rod at one end, the moment of inertia is equal to 1/3 ma squared. Now, what happens if the axis of rotation is moved to the center of the rod? So that means if this is our rod, the axis of rotation will be at the center. And let's say the element would be here, and this will be our x. So this will be our axis of rotation, and the distance from the axis of rotation to our element would be x. And this would still be dx. If we have the same rod with length a, now the limits of integration will be from negative a over 2 to a over 2. So that means the moment of inertia Iz will now be equal to x squared rho dx, but the limit of integration will be from negative a over 2 to a over 2. And this will be rho x cubed over 3 evaluated from negative a over 2 to a over 2. And as you will notice, the result will be different. In fact, the moment of inertia about the z-axis, if the axis of rotation is at the center of the rod, will be equal to 1 over 12 rho a cubed. Or in terms of m and a, this becomes 1 over 12 m a squared. So you will notice here that the moment of inertia of the same object doesn't only depend on the mass of the object, but where the axis of rotation is placed. In a more practical sense, it's easier for this object to be rotated when you rotate it about the center than about its end. You can try it at home. You can get your pen right now and try to rotate it about the center and compare it when you try to rotate it when you hold it at one end. So as you will notice, it's easier for you to rotate your pen about the center than about one end. So those are the things that you need to consider when you're calculating your center of mass. So that's it. That's the moment of inertia of a thin rod of uniform density. Thank you for watching. I hope you learned something today, and I'll see you guys in the next video. Bye bye.